I would like very much to thank the Inamari Foundations for giving me such a deep honor. Today, I'm going to talk about the evolution of OLED display technology. OLED stands for Organic Light-Emitting Diodes. In many ways, it's a journey of my life. So I'm going to tell you a story. I'm from the Hong Kong University in Science and Technology. I've been there for 5 years. So my own revolution, just very briefly. I came from Hong Kong. Hong Kong is in the south of China. It's a very small place, measuring 20 miles by 20 miles. Hong Kong, as you know it, as most of you know it, is a very bustling city. It's a city of lights, beautiful lights at night. But Hong Kong in the last couple of months is very chaotic, in turmoil. I'm sorry to say that, but I would like to ask for your support and understanding of the Hong Kong situations. And I also would like you to come to visit, if not now, in the near future. I came from a town in the northwest part of Hong Kong called Yunnan. And in the 50s, Yunnan was quite a bustling town. The main street, as you see here, was lined up with shops, restaurants. The villagers from nearby villages would come there to enjoy the morning tea or sell their goods. And that's the place where I grew up. I actually grew up in the village, nearby. And today, I moved to the southeast, to a university is only 25-year-old, and continue to do my research there in organic LED and other subjects. So, my village, and this is my the house built by my grandfather in 1921, almost 100 years ago. It's still standing there. And the reason it was standing there because it was made of very good materials, the bricks. The bricks was actually made in the kiln that owned by my grandfather. So he probably chose the best bricks and built the best house for himself and his family. And that's why it's still standing today. And nearby we call our old house, is the village shrine. It's a one-room building with a very small room attached to it. The small room is a one-room schoolhouse where I first have my first taste of education, 5-year-old. And I probably spent a few months there learning very simple Chinese. But that's how I started in my education pathway. So my early educations, I went to a primary school from 1953 to 59. The school was built in 1951. And my father, who is very influential in the town, particularly in education matters, that was responsible, the founding father or members of the school board. So he was a very important person to the community and also a very important person to me. But he also had very wild connections. And as you can see here, he was with Richard Nixon, the Vice President of the United States. I don't know how that he could invite the Vice President of the United States to visit his primary school in a remote place in Hong Kong. He was pointing to Richard Nixon. I think he was telling him what to do at that moment. I'm not so sure. But my family has a very special connection with the President of the United States. Not only my father had a chance to meet with the Vice President who later became the President of the United States. And here is my son. He had a chance to meet with President Obama. That was in 2011, when Obama was running for re-elections. I'm sure my son has something to do with his being re-elected. Again, I'm not so sure. So my father's generation, my son's generation had a chance to connect with the President of the United States, but my generation, no. So moving forward, after leaving Hong Kong, I went to the University of British Columbia in Vancouver, Canada, to study chemistry, and where I had the opportunity to do research, and beginning to do research with Professor Ogrislos. I don't know how I got into research, but I was very interested in building things. I was very proud of myself to build a piece of equipment out of glass, doing glass blowing all by myself. So I thought I would, I could make a living as a glass blower, but I'm glad I didn't do it. I moved on to higher educations. So after 3 years, I moved on to Cornell University to study physical chemistry under Professor A.C. Albrecht, and we call him Andy Albrecht. Of course, I learned of sciences from him. He's an expert in molecular spectroscopy. So I learned a little bit of spectroscopy, some solid-state physics, and under his directions. But he really did not direct me to do experiments. He's just there for me to ask questions, if I need to ask questions. He's trying to train you to be independent researchers. But most importantly, he taught me how to be a good human being, the humanity, and with a strong tilt towards liberalism. So he taught me to read the New York Times. It's probably the most liberal newspaper in the world. Then I went to Kodak right after the graduate school. I spent 31 years there. And as you can see from this picture, I really enjoy my work, and I was quite happy there. And after 31 years at Kodak, I moved on to academia. I was fortunate to have the opportunity to become a faculty member in the Department of Chemical Engineering in the University of Rochester, and then following that, coming to Hong Kong to be with the Institute for Advanced Studies at the Hong Kong University in Science Technology, where I'm still there now. So that was my very quick personal evolutions. Now I'm going to tell you the evolution of display technologist. So in this diagram, the horizontal axis is the year, starting from 1950 to 2030, projecting into the future. And then on the vertical axis is the dimension of the display in inches, the diagonal of the display. So the small display can be as small as less than 1 inch, and the big display, like this one, can be hundreds of thousands of inches. So in the 1950s, all we had were cathode tubes, big boxes. And that technology kind of lasts almost like 50 years. And until 1990 or so, the people want to have bigger televisions. But then they're getting heavier and heavier and heavier. You cannot even get into a small apartment. So the technology has to be replaced. And also, at the time, there was an evolution in computing. So portable computing is very important. So we had to come up with a technology that allow you to be portable. So that's where the flat panel display come in. So the CRT become obsolete, and then the flat panel display start coming in. And there's quite a few flat panel display technology. All I'm going to talk here is the LCD. So the LCD can be made small and also can be made very large. For the small one, they were used for the cell phones, the laptops, below 10, between the several inches to tens of inches. And they can also make very large TVs, typically on the order of 55 inches, 65 inches, or even bigger. So I put it, say, below 100 inches. And OLED, which come in about 2010, so that's about almost 20 years after the LCD. OLED find that the technology can be used for both the small display as well as the big display, just like the LCD. So OLED really was here to compete with the LCD because LCD is already existing. And as I will tell you later on in my talk, the competition is going quite well for OLED. And OLED has also another features, which is that it can be folded, it can be rolled, and so on. It can be curved. So it has a form factor which allow you for newer applications, like something that you can wear, like the watch and the other display as well. More recently, just in last year or two, there's another technology that came along, and that is called the micro-LED Light-Emitting Diode. And this is based on inorganic gallium nitride, the materials. And that technology, because you can tile the display together without the seams, and so we can make as large as you like, as you can afford to pay for it. And that display technology, the one at the upper corner there, almost have no limit in size. So they can go to 1,000 inches, more than 1,000 inches, but they cannot go small. So at least not now. So OLED and LCD can compete very well against each other, and we don't have to worry about the micro LED competing in the small dimension displays. So because CRT is such an important technology, even though it was obsolete now, I want to just briefly mention how the discovery came about. First of all, there is a discovery of electrons by J.J. Thomson back in 1985. And he was given a Nobel Prize in 1905 because of that. Just imagine discovering the electron, which we use for the electricity today. And then a few years later, Karl Braun used the electron to hit a screen that has a phosphor on it, and so that you can produce an image on the screen. And that's how the CRT2, or the modern TV, was the first discovered. So he won a Nobel Prize in 1909, but not for the display that he invented, but for a telegraph. So you can see, if you're smart, you can do many things and still get a Nobel Prize. So that was the CRT. So the problem with CRT is that it's very heavy and very thick, just because the technology was based on one electron gun. Okay. In other words, you have one addressing element for all the picture element we call pixels on the screen. And the screen can have million pixels, but you have only one gun. So the gun has to be directed to the screen using a magnetic field or electric field. So in this CRT technology, the thickness is proportional to the screen size, and the weight proportional to the screen size. And so the limitation is that it cannot be scaled to large screens. Here comes the flat panel display technologies. The difference there is that for each addressing element, you have 1 pixel. So you can compact them into a flat screen, as shown in this diagram on the right here. So the thickness of the screen can be only a few millimeters. In fact, for OLED, it can be less than 1 millimeter, and that's why it can be rolled. So this is literally a revolution rather than evolution in display technology, going from the big and fat and heavy to thin and light. So the LCD was the dominant technology in the flat panel displays. It was discovered for the display technology. LCD is known for a long time, but for display applications, it was first discovered in RCA laboratories in the 1960s. First, by Williams, he basically observed that if you apply a voltage to an LCD liquid, it can get cloudy. If you apply voltage to it and we remove the voltage, it can be transparent. So just a optical phenomena, but you can distinguish whether it's light passing through or not passing through. And a few years later, George Hellmeyer took their inventions and make a clock out of it. And that's the first LCD clock that he made, and that is him in the 1970s, I suppose. For this invention, he was given the 2005 Kyoto Prize, just to make that connections. So the evolution of LCD took 50 years, as you can see in this timeline chart. It started with Williams and Hellmeyer's discovery in the 60s, and there's other important discoveries, like the twist pneumatic the liquid crystals by Martin Shade and Helfrich in the 1973, I believe. And then the active matrix backplane using amorphous silicon, also in the 70s. And around the end of 70 was the beginning of OLED. So we were behind by about more than 15 years. And then after that, you have the display development. You have the one important milestone was the development of the blue LED by Nakamura, Akasaki, and Amano. The three of them won the Nobel Prize a couple years ago for that discovery. And because you have the blue LED, you also can have the white, and so therefore they can use the LED as the backlight for LCD, and that was very important. And after that, there's different LCD display technologies, but mostly important but minor variations. The important development was that about the 2010, the Chinese in China beginning to make huge investment in LCDs, and the price drops as a result. And today, you can get a 65 inches LCD, at least in the United States, for about $500. So it's very inexpensive for a large entertainment technologies. So roughly that was the timeline of LCD. So you have some key developments, and also you have huge investment to drive the price down. So the evolution of OLED. This is mainly to challenge LCD. because LCD is quite a good technology and it works quite well for display. But it also has drawbacks. Otherwise, would not be able to overtake them. So what's the major difference between LCD and OLED display? So this is a picture of LCD. There are stack arrangements. It has multiple layers. The key is the LC layer in the middle. Where you apply the voltage, it can turn the light, it's a shutter, so you can let the light go through or you can shut it off. So LCD is a shutter. And you need a backlight. And the shutter is to shut off the backlight. And you have the other layer. The one important layer is the polarizer. You have two of them in the front and the back that allow the LCD to act as a shutter. So one of the major drawbacks is that the light is always on, the backlight, at least for the prior generation of the LCD. The newer generation, they can turn the backlight on and off depending on demand, all right? But we can, don't have to be concerned with that for now. But the biggest problem is that when you turn off the LCD, some light can still leak through. Okay, it's not 100% shutter. And this little amount of light that leaks through can degrade the image quality of the TV quite significantly. In other words, they cannot achieve a perfect black. For OLED, it's a light emitter. It has, at least conceptually, we only require 2 layers plus 2 electrodes and a support substrate. When you turn on the voltage, allow the current to pass through it, the LED, the device produces light. Okay? So when you turn it off, the light is off. So the contrast ratio, we call it the native contrast ratio, can be infinite, practically infinite. But the LCD, at best, may be 1,000 or a few thousands. And that is a difference. But that is enough that your eye can tell the quality between the two displays. And this OLED stands for organic light-emitting diodes. So where the organic coming from? So the traditional, conventional, the light-emitting diode is based on inorganic semiconductors, as you can see in the picture on the left. Basically a point light source coming from a very tiny chip, tens of micron on the square. So it's a point light source. It's a crystalline inorganic semiconductor. The application is for lighting, backlight for LCD, and also for the billboards. It's very defined application there. For the organic LED, it's an area light source instead of a point source. It's made of amorphous organic thin films. It can be used in smartphones, televisions, and wearable watches. So real difference is that you can process the organic LED in an area. So that's why it's very suited for TV and flat panel display applications. And the fact it can be turned on and off very quickly is also a very important feature. So today's OLED display, the products ranging from televisions, you can buy 88 inches 8K televisions from LG for a very high price. There's also laptop made of OLED display, the tablet, and the most important application, it turned out, is in the cell phones. You also have application in the watches, the AR and VR applications as well. So from this figure, you can tell that OLED covers a very broad range of application. And that is one of the reasons it can be successful, just like the LCD. If you are only able to do the large area, or only able to do the small area, or only able to do one color, then you cannot cover such a wide range of applications. And on top of that, OLED has a very unique quality, which is, the display quality is excellent. So in 2013, the television was first introduced, the OLED TV. And this was me in front of LG's television. I'm not a salesman for LG. It just so happened that I was in a store in Hong Kong, and they first introduced it. So I just went down there and take a look at the TV, and I got a picture taken there as well. The price at the time was more than $10,000 when it was first introduced. But today, at least in the US market, you can get the same television for about $1,000. So it's the effect of 10 reductions in price over the last 6 years, which is quite remarkable for a display technology. And we look forward to further reduction in price in the OLED product in the future. So I want to show you what is in the future. And this is LG commercials. They loaned it to me. You can see a display coming out from a box. That is the box. And the display is coming out at a push a button. This is particularly good if you have a beautiful window in your bedroom or in your living room, and you just place that box right in front of your window, and you can look outside if you don't want to watch a TV, and then you can raise the TV if you want to watch it. The reason you can have this kind of new TV, because OLED is so thin, it can be rolled up. Also, OLED, because of thinness, it can be folded. So the foldable phone in the market now, which sold by Samsung and Huawei, maybe a few others. So these two are products today, but they're kind of expensive. So now I'll go back a little bit to tell you a bit more about the discovery of OLED. The OLED was based on electroluminescence. The early work was done back in the 60s, just like the LCD. And in this paper here, published in 1965, the device was made of anthracene crystals sandwiched between the two electrodes here. And if you apply a voltage on the order of 2,000 volts, you can get a very small current on the order of 10 to the -5 amp per square centimeter, very small. But you can still see light coming out. And that's proof that the recombination of electron coming from the cathode and the positive charge coming from the anode, the recombination would give you light. And this is the evidence of it. And it was a blue light. So the first blue LED is actually organic, not inorganic LED, I think. But it requires high voltage and low current, even though the efficiency is high. So there's no applications. There's no practical applications. So here is how I came in. I spent a few years at Kodak when I first joined the research lab to work on organic solar cells. It was a total failure on organic solar cells in terms of applications. I did not make anything useful. But I did discover something quite important, and that is I can use a two-layer structure, or we call it the PN heterojunction structure, to enhance the photogeneration efficiencies, in other words, the solar cell efficiencies. The reason we could do that is because we have this junction right here. This is an energy level diagram I don't want to get into. That if you have anything absorbed in this region, the light absorbed by the materials would create excitons. And the excitons, which can be dissociated by these junctions to separate the charge into holes and electrons, and that be collected in an external circuit. So it was a quite remarkable in terms of accomplishment at the time, because I achieved a 1% solar cell efficiencies, even though at the time the solar cell efficiency is more than 10%, based on inorganic semiconductors. But nevertheless, by the proper choice of materials, and with the thickness adjusted to about only 60 nanometer, I can get a very decent device performance. But only drawback is I get a 1% efficiency, competing with 10, 20% at the time. So the reason it was so inefficient, because the layer thickness is so thin. It doesn't absorb enough light, and that was the major problem. And I cannot increase the thickness because the transport of charges become a limitations. So I fail, and I move on. So I move on to organic light-emitting diode. Based on the same structure, nothing changed. The same structure, almost the identical thicknesses. But now, I inject charges, instead of separating charges, and inject charges into it. Electron from the cathode, the holes, a positive charge from the anode. And the recombination takes place here, just because there's a barrier there that the charge cannot cross over. So they have to recombine. And the region for recombination, it can be so thin. So thinness doesn't matter. Actually, it helps because it requires lower voltages. All right. So because of that, and with proper choice of material, this is very important, proper choice of material. You cannot just randomly choose any material. You can get very high efficiencies. So with this bilayer structure, very thin films, and I'm also engineering a very important cathode, magnesium silver, and then you can derive very high efficiencies, I would say modest efficiencies, and at a low voltage. And another feature is that the very fast response. So it's perfect almost for display application with this kind of attributes. So this paper was cited over 16,000 times. It's quite remarkable. And just to give you a little statistics, so the paper get published here, and then the number of citation goes up. And the regions that cited this paper, that China now, because they have more researchers that they're on this field, and it has the highest station, followed by Japan and South Korea and the United States. This kind of reflect the development of the technology in that regions. And 2 years later, after publication of the first paper, I went ahead and come up with a scheme. We called it the doped organic thin films. What I did was that in somewhere in this layer here, I introduced or inserted in the layer, which is doped with fluorescent materials. And this fluorescent material would be used to change the color coming out from the main emitter material that we call the host. And with this scheme here, we can produce green light and red light with high efficiency and maybe even longer lifetime. But we were not able to produce blue light at the time because this host material can only generate green light. But the principle is useful for producing RGB. If you have a blue host, you can produce all three of them. So what my accomplishment, the contribution was somehow to make the electron-hole pair recombination to be more or less 100%. So every electron has to meet the holes. But then after recombined, you can go through two channels. One is called single channel, another one triplet channels. So all my prior work was based on this single channel, which has only 25% efficiency, and that was the major limitations. And I wish I had found some way to utilize these channels, but I didn't. And of course, the other efficiency factor I'm not going to get into. The another milestone paper that was published in 1999, almost 12 years after I published our first paper. And this by the group from Princeton and University of Southern California, by these three gentlemen, Bortles, Forrest, and Thompsons. What they did is that they were able to use the triple channel, which has 75% pathway, so that together they can collect most of the recombination and turn it into excitons and turn it into light. All right. So they created a pathway forward to have 100%, we call it internal quantum efficiency. Every electron that comes in can produce light. And this is a major breakthrough. And that is also the reason why that we have the display technology today. Well, organic LED has some lifetime issues because it is emissive, and you go through the excited state, and not all the excited state will turn to light, and some of them can turn into degradation products. And so the OLED can degrade. You can drastically improve the lifetime without changing the materials. You're just changing the device architecture. Here we have Professor Junji Kyoto from Yamagata Universities coming up with a multi-stack structures, basically stacking each unit, all multiple units together in a series. So the current going through it, it would produce light in each of the unit, and the light would be summed to produce the light to go outside of the device. So this way, you can have little current going through it, but more light at the expenses of higher voltages. But this is a key development. It enables the current television technologies. So what do we have? We have OLED, for the OLED technology, we have a low voltage drive, high efficiency now, full color using the doping scheme. Fundamentally, it's fast switching, much faster than LCD. High contrast, because we can turn it off to have black as black. We also have wide view angles compared to LCD. We still have a little problem. The lifetime can be improved a little, but it doesn't prevent the technology to moving forward in commercialization. Like, for instance, we use the stack structure to improve the lifetime. So the evolution of display. So we felt confident that we can compete with LCD now. So, I'm sorry, I forgot the sequence, but I'm going to take you through it. First, you have the iPhone. The iPhone measures about roughly 6 inches in diagonal. And within the screen, you have 8 million pixels, color pixels, and about 50 million transistors to operate this tiny screen, okay? And each color pixels can be switched on and off rapidly, and therefore you can see the images. And that's how complicated it is. But it all can be done monolithically, and that's why it can be made so cheap. You don't do it one by one. If you take one of the pixels and you blow it up, you find that all the multi-layer structures, your transistors there, the organics is there, and then you have the substrate, which can be plastic, and then you also have an encapsulation layer to prevent the oxygen and moisture from coming in. That's how you can protect the OLED. And each of the OLED stack, instead of consisting of 2 layers now, it consists more than like 5 or 6 layers. So it's very complicated, all right? And each layer has its own set of materials. And I'm showing here the 3 emitting materials, red, green, and blue. It may not be the exact structure, but they're kind of complicated in molecular design, because you have to make sure they emit in the right wavelength and with the right bandwidth and so on. Okay, so there can be as many as 20 molecules, including the metal electrodes and other, in the stack. But they're all done by vapor depositions at this time. So I want to go through some of how we develop the display from very simple one to more complex ones. So back in the 1990s at Kodak, we said that, okay, we have enough fun with the material development. Let's try to make a display out of it. So we tried to make a very simple 100 by 100 display. And that means 10,000 pixels instead of 8 million pixels. So the simple way to do it is that you evaporate, you prepare the ITO electrode on the glass support, you evaporate, and then you pattern it into rows, and then you put down the organic layer, and then you put down the cathode layer by evaporations, and then you do the lithography to pattern the top cathodes. It's easier said than done because patterning the cathode can disrupt the underlying organic layer. So that was a problem, and the result that we achieved was not that good. The display was very defective, as you can see here. But that was in 1990. So a few years later, I came up with a way of patterning that doesn't require photolithography after we evaporate the organic thin films. We basically put the shadow mask on the ITO anodes before we deposit all the organic layer and metal layers. So organic layer and metal layer will deposit without the interruptions. And by evaporating the metal from oblique angles, we can produce a gap here, and a gap here. And therefore, we can isolate the cathode to give you the display. And Pioneer, the Tokuho Pioneer, took it one step further. They come up with a more elaborate scheme to isolate the cathodes, and they were even more successful. So they go with the process, and then they develop the very first passive matrix OLED. That is the very first applications in using OLED display. Motorola use it for cell phone, and they also use it for the audios. So these are very simple ones. And now if you have to move to the more active matrix display so that you can get a higher resolution, larger area, and so on. For reason is that if you use the simple passive matrix display, you're only limited to about a few hundred lines. With the active matrix display, which you incorporate the transistor with each of the OLED pixels, then you can infinitely scale it to 8K, 4K display, and that's how it move on. So back in the 1999, 2000s, we came up with a pixel scheme right here that not only for driving the OLED display that gives you a very high uniformity. And so today, in your cell phone, you have 7 transistors, 1 storage capacitor for each pixels. At the time, we only have 2 transistors and 1 capacitor. Okay, so technology moving forward. So in Kodak, we had we developed the display. The first one is the 5 inches. Basically, we want to show it to the manager to impress them that we can actually make display. And we team up with Sanyo in this country here to make that. They provide the backplane, we provided the OLED technology. And the first product came out a few years later. In 2003, we used it for the phone, but unfortunately, it's very costly to make a display, so it's not a good business, so we had to withdraw that product. Making a product requires many, many people, and this is a small group of people in the research lab, trying to pull this off. And the person who really was in charge of this to drive the commercialization of OLED for Kodak is Dr. Rajaswani, and I just want to acknowledge him for his work. So, OLED display was introduced in the market. You have the cell phone, you have the TV. Here I want to show you the product that was proposed by 2 major corporations. One is Samsung, other one is LG. Samsung here, the display quality is more or less the same. There's not a big differences. The Samsung chose a technology, we call it the LTPS TFT technology. And they also used shadow masking for patterning the RGB side by side. This approach led them to failure. So they commercialized it for maybe a couple of months and they have to put the product out. Simply because it's very difficult to use the pattern RGB technology to produce large area display. That patterning is not mature. And so as a result, they cannot produce panel cheap enough to make it. In contrast, LG has no problem that they use a metal oxide technology, and then they use RGB, using the white OLED, using conventional color filter to produce the color pixels. They take a hit in power consumption, but they can manufacture it. Okay, as a result, they are very successful in manufacturing, and they are the only suppliers, credible supplier of OLED TV today. So, in very short summary, I want to show you that in the first 20 years, I was very engaged in the material development, starting with my employment at Kodak, the OLED discovery later in the decades. This is the equipment that I use for making most of my devices. In 1987, the first paper was published. We make the first passive matrix display, the one I showed you, that didn't look too good. And the other display, the older technology came in, like the polymer LED. And the Kodak, we also use the OLED for printing applications. The triplet emitter that enable 100% efficiencies didn't come in until 1999. And the phone, the first cell phone was about 2000. And then from then on was the display technology developments. So in the next 20 years, okay, from 2000 to 2020, so we had the first micro display product, the Kodak camera, the Sony PDA, the first the so-called the smartphone, not the small cell phones, and the first OLED TV by Sony. And then Samsung decided to mass produce OLED for their cell phone applications. And then the TV comes in 2013. And now the mass production starts in China. So if history is a guide, then you will be able to enjoy OLED the TV, cell phones at a lower price in the near future. Okay. This is the 88-inch television made by LG, and this is the rollable ones. Along the way, there's other development by other companies as well. So it has been a very fulfilling journey of a personal and scientific discovery for me, starting from a village in Hong Kong and ending in a discovery that leading to OLED. Along the way, I had the support of a very free, strong woman. My grandmother, my mother, and my wife. And I also have a wonderful family, and they're all here. Thank you very much.
Thank you very much, Dr. Tang. Please move to center of the stage to receive flowers.
Thank you.